In this video, we are going to discuss similar figures and how to determine if two figures are similar to each other. Well, what's a similar figure? Well, I'm glad I asked because I've got the answer up here. Let's check it out. Similar figures are figures that have the same exact shape, but they don't necessarily have to have the same size. So you could think of it as if you had like an action figure made up of yourself for some reason, and it was much smaller, but it had all the same features that you did, the same proportions. So your nose had a ratio of like 1 to 10 to your actual nose, and your arm length would also be 1 to 10, and so on and so forth. So everything is shrunk down or blown up at the same ratio, same shape, not necessarily the same size. So the two components that make figures similar are, 1, corresponding angles are congruent. So the corresponding angles in any two shapes have to have the same measure in order to be similar. In addition to that, we've got to have the corresponding sides make the same or equal ratios. The word we use for that when we have equal ratios would be a proportion, right? Or the sides are proportional. So to check and see if sides are proportional, we simply find the ratios of corresponding sides and see if they're all the same ratio. Let's do this, shall we? So I've got a triangle TQR or QTR, however you want to say it. And in that triangle, I've got 3 angle measures given and 3 side lengths given as well. Keep in mind, this triangle is not at all drawn to scale of an actual triangle with these kinds of degree measures. I just want to point that out for those hardcore math fans who are out there saying, you can't have a triangle with those degree measures and those sides. I know, but we're going to use it for the sake of argument, okay? Here we go, let's do it. So we've got another triangle and another one over here, and we're asked, is either triangle similar to triangle TQR? So we'll start with just this one right here. Let's just start by lining up the corresponding angles. Angle C and angle T both correspond to each other. C would lie right on top of T, and they're both 31 degrees. Therefore, we're off to a good start. Angle B is congruent to angle Q, both being 120 degrees, and angle A, being 29, corresponds and is congruent to angle R. So we've satisfied step 1. We've got congruent corresponding angles. That does not necessarily mean that we have similar figures, right? Depending on the shape of the object, we'd also need to show the ratios of the sides are equal, or we form a proportion. So let's take a look at that now. Well, we have side length BC and QT correspond to each other. So I'm going to set up that ratio. That would be the smaller triangle to the larger triangle. You want to make sure that you stay consistent. So if we go smaller to larger triangle, we've got to keep doing that, or else we're going to be taking reciprocals of things and potentially giving ourselves false conclusions. So we've got 6 to 8. I'm going to simplify that. We would divide the numerator and denominator by 2, and that would give us 3/4. So that's comparing BC to QT. Now, and maybe I'll write that out. We're comparing the length of BC, and the notation for length of BC is BC without a segment on top, to the length of QT. Great. Okay, then the next one we're going to do is we'll do this guy, BA to QR. So BA over QR. Those lengths are going to be 9 to 12. And we'll simplify that again. So we'll reduce it to its simplest form, divide the numerator and denominator by the GCF, which is 3. 9 divided by 3 is let's see, yeah, I was about to write 4. In most places, 9 divided by 3 is 3. Okay, so we get 3 over 12 divided by 3 is 4. Ooh, so far we have the same ratio. Don't stop there. We need to show that all the sides are in the same ratio or proportional. So we have what's left. We have AC corresponds to RT. So we're going to compare those two side lengths. Sorry about the little bit of slantiness in my writing, but that's pretty much par for my writing course. Now AC is equal to 15, and we are going to compare that to RT, which is 21T. We're going to divide numerator and denominator by the GCF, 5. 15 divided by 5 is 3. 20 divided by 5 is 4. And what we have now seen is that this triangle has 3 corresponding congruent angles to this one, and all the corresponding sides have the same ratio of 3 to 4. So this triangle to that one has a ratio of 4 to 3, this one to that one, 3 to 4. Sweet. All right, so a 3/4 ratio. How do we state if two things are similar? It's very similar to how we show, get it similar, congruence. So you would state triangle, and I guess we'll do RQT, and then you just write the squiggly part, similar, not equal to, not congruent to, but similar to. Start with the corresponding letter or point A, B, C. Triangle ABC, and that's a similarity statement. That is how you show two triangles are similar. Now I'm going to go a little bit further and discuss this triangle over here. This gives you a great, in my own opinion, start on the idea of similarity, but let's keep going, shall we? So we've got this triangle over here, triangle PAL, P-A-L. Again, we're being asked, is this similar to that right over there? Well, the first thing I notice is that angle P has a measure of 33 degrees. And that corresponds to angle T, right? Angle T is the second biggest angle in this triangle, and angle P is the second biggest angle in this triangle, so they correspond. 33 does not equal to 31 right away. They are not the same shape, and therefore, they are not similar. So it can be that simple. You could also notice that angle L is 27 and angle R is going to be, well, 29 degrees. They're not the same measure. So again, not similar. And there's another way. If we compare AP, which is 5, to the corresponding part QT, which is 8, we get a ratio of 5/8. But now compare LA to RQ. Well, LA is 7, but RQ is 12. And these are both in reduced form, and 5/8 is not equivalent to 7/12. So they don't even have the same ratios. So while these triangles appear to maybe be close in shape, they're not similar to each other. So we don't have a similarity statement to write like we did for this one. That's all we've got for similarity, folks. I want to point out that we used triangles to show similarity. You can do this with rectangles, pentagons, hexagons, any kind of polygon you can think of. All you do is compare the corresponding sides and see if their ratios are the same, always going from one figure to the other, staying consistent, and you also compare the corresponding angles to see if they're congruent. That's all there is to it.